Easy.
Yeah, sixth grade. Like when you look closely to the TV series, you always like really bad
And we can just do this.
What is that? What is that?
OMG. We can do COCOMG. Oh, I was going to read that. You did it? Oh my God.
It's like
I appreciate the effort. Did you use that? Okay.
What?
It's like the equation you gave the notes if you're very and you're not like maybe you'll be very specific looking for G. It's yeah, it's been not.
What if we just make a molecule?
You should ask for it. You should make me an MS, please.
So my raise volume.
Email people. I didn't get anything back from the lab, so my tab. We just. Well, I'll ask today when I go.
Yeah.
I think this is right.
I don't have to. This
is actually the same board because what I was
And then so I say things on my.
but this is like.
You know what I wanted to be? It was like middle of July, I took claim to my dad, so I want to be a full grown.
Yeah.
So my dad was like,
Which really extensive versions of our cultures.
I don't have anything.
Welcome to Lab 9. This lab, we will be solving boundary value problems on Python. So we went over how do we solve it analytically in lecture on Monday. And in this lab, we'll do it in Python. So these are a review of the types of boundary conditions and the homogeneity of boundary condition and boundary value problems. Let's look at a practice example with type 1 condition where we have the boundaries of the original function at the two ends. So here we have a second order ODE. In order to solve it in Python, we need to reduce it down into a system of first order ODEs. So to do that, we'll need to first define auxiliary variables. So make W0, define it as the original function y, define W1 as the first derivative. Then we take the derivative of the auxiliary variables. So W0 prime is y prime, and y prime we already define as W1. And then we take the derivative of W1, and that's y prime's derivative, so y double prime. But we don't have y double prime defined in terms of W. But what we can do is to rewrite the original ODE in terms of y double prime. So move 4y to the right, we have y double prime is equal to minus 4y. So we have y prime is equal to minus 4y, but we want to rewrite the y in terms of w, and y is already defined as w0. So we have minus 4 w0. So that we have the system w0 prime is equal to w1, and w1 prime is equal to minus 4 w0. Okay, and then we can rewrite the boundary conditions. Boundary condition says that we have y0 is minus 2, and then y of pi over 4 is equal to 10. And then y we define as w0, so we can rewrite it as w0 of 0 is minus 2, and w0 of pi over 4 is 10. And so this is our new system that we want to solve for in Python. Any question on this part? Okay, and in this lab, instead of using solve IVP, initial value problem, we'll need to use solve BVP for boundary value problems. This is a little different from the solve IVP in terms of the things that we need. So the first thing we need is the ODE system. this is the same as solve IVP. So how do we rewrite this system in terms of ODEs? So because we have this system, we can write in Python dw0 dt is equal to a lambda function of the independent variable, in this case x, comma all the dependent variables. So dependent variable, we have w0, w1, colon, and then it is equal to w1. And for dw1 dt, we also define it as a lambda function of independent variable x and dependent variables w0 and w1. And then it is equal to 4 minus 4 times. In Python, we need to use stars as times. So if you don't use star, it will be a syntax error. So minus 4 star w0. And then now we have individually defined each first order ODE. We want to define the ODE system. The system is also a lambda function. It takes in the independent variable x and then a list of dependent variable z. So this is independent variable. This is list of dependent variable. And then it takes in a list. I'll just write it here as one line. So the list will contain dw0 dt evaluated at x, and then unpack syntax of z. So we're unpacking all the parameters of z into w0 and w1, and comma the next item, so dw1 dt evaluated at x, and then unpack syntax z. So these are the same as solve IVP. So be sure to know how to do this so that you are well prepared for the midterm. And then the other thing that you need is to define boundary conditions. And the boundary conditions in our case is y0 is equal to, let's see, minus 2, and then y of pi over 4 is 10. To define boundary conditions in solve IVP, it will require you to rewrite it in terms of something is equal to 0. So y of 0 plus 2 is equal to 0. And then y pi over 4 minus 10 is equal to 0. So what Python will need is this part. They will automatically set this to equal to 0. And the convention that it needs is that, so these are the convention by Python that we need to follow, is that it requires the boundary conditions to be a lambda function. So BC is a lambda function instead of a list. Because in initial value problems, the initial values are in a list, but here, boundary condition is a function, not a list. And the function takes in 2 arguments. So the first argument is y left. So this is everything that's on the left boundary. And then y right, everything on the right boundary. It contains typically 2 arguments for 2 second order ODEs, or a system of 2 ODEs. So the first argument, or the 0th index, is the original function. The original function, so y left will be y of 0, and y right will be y of L. The second argument, or the first index, it contains the first derivative. So it will be, so y left of index 1 will be y prime of 0. Y right of index 1 will be y prime at L. So in order to rewrite this analytical form into Python, we'll need to make it in the y left and y right syntax. So we match this. So y0, here's y0. So it will be y left of index 0 plus 2. And here we have y of pi over 4. Pi over 4 is the right boundary, so y of L. So we have y right of 0 minus 10. And that's how we define the boundary conditions using a lambda function. And in the list, we have y left of 0 minus y0 left, which I define as minus 2. So basically plus 2. And then y right of 0 minus y0 right, which is 10. So this is the second thing we need, the boundary condition. Then we will need the x, so the interval that you're defined on. So usually when you have a boundary condition, you have an interval x. You'll have x at the left-hand side, which is x equal to usually 0. And on the right-hand side, y equals to L. In this case, L is equal to pi over 4. And you'll need to define points in between them. And you can use a range or lin space. And finally, we'll need some guess. So this is different than the initial value problem where we do not need a guess. But for boundary value problems, we'll need a guess. And the guess has a particular form. So because we have a system of two ODEs, so ODE 1 and ODE 2. So the final result will also have two components. One is the original function, and one is the first derivative, each defined on the interval x. And the interval x will have defined many points in between them. Let's say we define 10 points. And then we have two columns. So for each of these points we defined, we need an initial guess. So what we need to initialize is a 2 by 10, and 10 is the number of x points matrix of initial guess. And we can define this as using np.zeros. So it will generate a matrix of 0 of the shape 2 times 10. Okay, so those are the 4 components that we need. And let's try to code this up from scratch. So first, let's look at what we need. So scipy.integrate.solve BVP. So if we do a question mark and run it, we'll see that what we need. So we need a function. So we can define the function using the syntax we just written. So here we have dw0 dt is equal to a lambda function of independent variable t, and then dependent variables w0 and w1. And then dw0 prime is equal to w1, so w1. Then second line, dw1 dt is also a lambda function of independent variable, dependent variables, and it is equal to -4 times w0. Finally, we write it into a system, so ODE system is equal to lambda function of t, the independent variable, and the list of dependent variable, we call it C. Of list, the first one we have dw0 dt evaluated at t, and then all the parameter of C. And then similarly, we have dw1 dt evaluate at t and all Z. To verify that it works, we can input some arbitrary number, so maybe 2, 1, 1, and it should give us a list of 2 numbers. So this shows that this whole thing works. Okay, so we have defined the function. Now we need to define the boundary conditions. So the boundary conditions, again, we'll need to translate it into these y left and y right. And the boundary condition must be a lambda function, taking in y left as a list, and then y right also as a list. And it returns a list of 2 boundary conditions. And the boundary conditions, we have y0, which is on the left, and its original function, so this 0 index, so y left of 0 plus 2. And then we have here on the right, still original function, so y right of 0 minus 10. Any question? And to make it more general, we can also define y0 on the left and then y0 on the right. So the next time we can just input the boundary condition like this. So y0 is equal to -2, and then y of right on the right side is 10. And then we can change these to, instead of +2, we can do minus y0 left. And then here we can also do minus y0 right to make it more general. Any question on defining boundary condition? So this is the hardest part of this lab. It's what's different than the self AVP. We define the boundary condition as a function with these conventions. And then we define the x, the interval. So x minimum is 0. X maximum is pi over 4. So np dot pi divided by 4. The problem didn't specify what number of x we can use. So we can use some x length that is large. So we use 1,000 points. So we can use np lin space to generate those points. So from x minimum to x maximum with 1,000 points. And you can verify by printing them. And finally, we need to initialize some guess. And the guess needs to be 2 by 10 or 2 by 1,000 in our case. So the guess will be np zeros with 2 rows and then x length number of columns. And we'll input all of those into solve BVP. So OD system, boundary condition, x, and guess. So the result says that the algorithm has converged to the desired accuracy. And usually what we care about is the y. But another way to, the simpler way to look at this is to index to the solution. So dot SOL for solution. This is a function, so that gives us the final solution. So we can write this as the BVP solution as a function, so f BVP solution. And then we can evaluate it at different x's. For example, evaluate at 0, evaluate at 1. And you notice that there's a list of 2 elements. The first element corresponds to the original function, and the second element corresponds to the first derivative, just like here. So first element for original function, second element is first derivative. So we can also evaluate at x. X is already a list of points, so we can also evaluate those lists of points. And then it has 2 elements. First element is the original function. Second element is the first derivative. So index the first 0th index, so first element. So this is the original function. And we can plot this. And this will be our final solution. So big X is subplots, change these to axes, set the X label as X, and set the Y label as Y. Any question? And we can compare it with the analytic solution. So at the analytic solution, we have Y analytic is equal to a lambda function of X. It's -2 times cosine of X of 2X plus 10 times sine of 2X. So we can also plot the analytic solution and label them. So X, F analytic, evaluate at X, and label it with analytic solution. No, I haven't run it. Y analytic. And so here we see only the analytic solution because they are overlapping. So if I make it a dashed line, you see that they are overlapping with each other. So the solved VBP achieve high accuracy compared to analytic solution. In this case, the analytic solution tells us there's one unique solution, and solved VBP indeed give us one solution. So any questions? Okay. But on Monday, we saw that we can not only have one unique solution, but we can also have infinitely many solutions or no solution. So for the same ODE with different boundary conditions, we have infinitely many solutions. But one thing to note, all these things are similar except for the boundary conditions, so you can change it up yourself. But if you look at the solution, solved BVP still give only one solution, but the analytic solution suggests that we have infinitely many solutions. So this is one of the drawback for numerical solution, is that numerical solution can only return one solution for you. It does not tell you if it has infinitely many solutions. So if you want to know if it has how many solutions it has, you must solve it analytically, not numerically. So when you got one result from numerical solution, it does not tell you how many solutions that BVP has. And then for the case of no solution, so analytically we define have no solution. If we solve it numerically, the solved BVP will still return one solution for you. But you have to identify that solution is not reasonable because it starts at 0, but it oscillates to 1e10. 1e10 in math is 10 to the 10. So the variation is too big, so you can identify it as a non-reasonable solution. So even though numerical solution returns a solution for you, it could be just a fluke. So you have to look at the analytic solution to identify that this actually has no solution. And one of the ways that you can identify false numerical solution is to look at its scale. If its scale is too large, it's probably a fluke. Okay, and you can try this practice problem to code up the solved BVP. I highly encourage you to code it up from scratch instead of just copy and pasting, because this will be important in your final exam. We still have time and ability. So we look at scale and make students. This is so. So this is. So the practice problem has one. So it shouldn't be big structure which seems.
Yeah. Because this is there's no this. I think some of the variables are. Because you take you define. Here is the one field. The first one is right the example. Here should be a plus sign. First problem has to be. Verifying the concentration of plus ones. So this out. So how do you get here to here?
Oh, okay, that's here, right here.
Yeah.
Maybe.
And so, this also right here, like just like the questions. Okay, that's why I look at, oh, so it starts here. As that's why I was confused, okay, thank you.
It's just not. Which is like.
It's so easy. It's so easy.
Like this because we're
See, I'm cultured. There's a banana that was shaped to a
Okay, are we all done with this problem? So to solve this problem, we need SciPy integrate solve BVP. And it requires the function. And to rewrite this function, again, we do make it a system of first order ODE. So we have dw0 dt is equal to a lambda function of x, w0, and w1. And then dw0 should be equal to w1. And dw1 dt is also a lambda function of x, w0, and w1. And it is equal to the original ODE separate y prime, y double prime. So we have -3 times y, and y we define it as w0. And then define the ODE system as a lambda function of independent variable x and list of dependent variable z. And we evaluate dw0 dt at x and then star z. So unpacking all the components of z. And then dw1 dt at x and star of z. And to verify if it works or not. So let's just input some numbers. The y0 is not defined. Oh, this should be w0. So now we return some values. So this works. Okay, next we define the boundary conditions. The boundary conditions must be defined as a lambda function, not a list. And it takes in y left and y right. And it is a list, returns a list. So the boundary condition we have is on y0 left is 7, and y0 right is 2 times pi. Here, the 0 means the order of derivative. So 0th order derivative is the original function. And evaluated at left is parentheses 0. Evaluated at right is parentheses 2 pi. So in the boundary condition, we want to write it in terms of something equal to 0. So this is y0 minus 7. And y0 is y left, the 0th argument, because the 0th one is original function. The first one is the first derivative. Minus 7, which is minusing the y0 left constant. And the second boundary condition is y right and the original function, so index 0 minus 0, and which is, oh, this should be 0, not 2 pi. So minus y0 right. And this is the boundary condition. And for x, it's from 0 to 2 pi. So x min is 0, x max is 2 pi. And then x length, we can define it as a large number, so 1,000. So we can use NP lin space to get points from minimum to x maximum at x length. So this should give me 1,000 points. Finally, we need to initialize some initial guess. And the initial guess should have two rows. The first row is the original function and the second row first derivative. So you should have a dimension of 2 times the number of points we have, so x length. So np dot zeros. So this should give me 2 rows and 1,000 points. And we input everything into function. We have ODE system, boundary conditions, the x, and the guess. Oh, why right? So I should put a underscore here. And then this gives the final result. So we index to the solution. So the BVP solution is a function. So we can plot the result. So x, and then the function evaluated at x, label it as the BVP solution. Must be the same dimension. So whenever we use the solve BVP function, it always returns always returns a list with 2 elements. First element is the original function. Second element is the first derivative. So we need to index to the 0th index in order to get the original function. So because we have a value error here, we need to index to 0. And this gives us the final result. And we can verify with the analytic solution. So f analytic is a lambda function of x, 7 times cosine of square root of 3 times x minus 7 times cotangent. We don't have a cotangent in Python, but we do have tangent. Cotangent is the inverse of tangent, so we do a divided by tangent. 2 times square root of 3 times pi. This is a constant that we solved for yesterday. And times np sine square root of 3 times x. So we have our analytic function, so we can plot this solution, analytic solution as well, and label it as analytic. And they overlap with each other. So if I make it a dashed line, you'll see that it's exactly on top of each other. So solve BVP gives high accuracy compared to analytic solution. And in this case, we have one unique solution. Any question? So the hardest part is to define boundary condition. So please practice how you define boundary conditions, even if you're copy and pasting. This is the most important part. Okay, then we can look at different types of boundary conditions. Here we have type 2 boundary condition where we have first derivative at both ends. So everything else is different, is the same, but the only thing different is the boundary condition that we define. So the boundary condition, remember that we're defining the boundary condition in terms of y left and y right, and its second element, or the first index, is the first derivative. So whenever we have a y prime of 0 is equal to 6, this tells us it's at y left of index 1. So let's try writing that out. So we have boundary condition y prime of 0 is 6, and y prime of pi is equal to 9, minus 9. The convention is that f left is a list and y right is a list. The first element is the original function y, and the second element is the first derivative y prime. So we have y of 0, y prime of 0, and then y of L, y prime of L. And to rewrite this in terms of Python language, using this convention, so this is y prime of 0, which is here, So it is y left of index 1 minus 6 is equal to 0. And here y prime of pi, which is y prime of L. So we have y right of index 1 plus 9 is equal to 0. So when we're defining it in Python, we have y left minus the constant 6. And then we have y right index 1 minus y1 right. Here the 1 denotes the order of derivative, so first derivative. Any question? And here we analytically solve it and we found no solution. But the numerical solution, again, always gives one solution. And you can determine that it's not a reasonable solution by looking at the scale. This is 1e8, so 10 to the 8th. So the variation is too large, so this should be discarded as no solution. When you have a mixed condition, you have first derivative at one end and original function at the other end. So in this case, we have y prime of 0 is 5, and y of pi over 2 is minus 5 over 3. So first we rewrite into something equal to 0. So y prime of 0 minus 5 is equal to 0, and y of pi over 2 plus 5 over 3 is equal to 0. And using the convention, we can rewrite in Python, this is y prime of 0, so y left of index 0. Oh, it is the first derivative, so index 1 minus 5 is equal to 0. And then here we have the on the right, so y right, we have the original function, so uses index 0 plus 5 over 3 is equal to 0. So that's how we define the boundary conditions. So at BC, we define y left of 1 minus, here is a constant 5. And then y right index 0, so this is the original function on the right, minus y0 right, defined also as a constant. Any question? In this case, again, we analytically found that it has infinitely many solutions, but the numerical solution only gives one solution. So it doesn't tell us if the BVP has just one solution, infinitely many, or 0. Can also look at trivial solutions. So this is a homogeneous ODE with homogeneous boundary values. And the solution for that gives just a 0. And this is an opportunity to demonstrate the why do we need initial guesses. So initial guess should not matter if it's reasonable. So if I do 0 plus 2, so if I make all the initial condition 2, it should still give me the same result. So this is what it gives me if I guess 2. So it looks zigzagged going up and down, but if you look at the scale, it's 1e minus 14. So this is 10 to the minus 14. That is close to the numerical roundoff error. So this will disappear if you set the y limit to say -1 and 1. Then you see that this is indeed the trivial solution, y is equal to 0. So even if you don't have that, you should realize with the scale that this is essentially just 0. Any question? Okay, and you can do the practice problem with this mixed boundary condition, and this will test your understanding of how to define complex, complicated boundary conditions.
This is
Okay,
Yeah, I was like, oh, here's the YouTube time.
like,
He's gonna take the test, also the grammar test, he takes a test, he goes, yeah, and I'm like, oh,
so for real. We need to have it. Index 0 is the.
oh, it's at index 1.
What do you think? The first one.
yeah.
Here.
We didn't have a.
Oh, sorry. So, here's how can I indicate the field now?
Yeah, so. 0 plus is.
What's zero?
0 is the one.
Did you pay $105?
That's so the index here.
This one.
Because it's gonna be 1 minus 0.
And so everything under that.
Print out.
So.
Print out.
So it's already in the.
Print out.
Is it just 1 minus 0?
1 minus.
Yeah, we put it.
And then this one I find
I
it.
guess to Yes, do it.
Oh, yeah.
I want to troll. I want to troll someone wears
How do you
like.
Is it a back boundary mix or right boundary? You just write one minus something. That's.
Why not?
And then, what else is this? You need to index it. And the index is dependent on the order of it's
Okay, and so here,
it's not done.
oh,
There's no stuff.
okay, so can I say plus?
We put his face on our face. Got a little circle.
And then, so what is this?
So first, that's one.
And then.
I don't understand what that.
So is there a left boundary function? Right?
This is the left.
Reason is because you have
Yeah.
1 0.
Okay, so how do I do this?
So first write down.
Yeah, I'm going to launch it.
Then the index is in the first thing or first function.
It's the that's, so that's indicating that it's, but I should define why.
You define that.
If we don't troll him.
Oh, okay, so I'm missing. Second, to get things out of the picture. And so this one is just.
That's very neat.
So now I don't need to solve it. Yeah, solve it.
We're like, I'm close to Helen. I don't want him to hit himself. He already doesn't really like it. I don't think he doesn't really. I was like, I love this man. Once he changed, he seems like maybe he was so cool. He met it. So. Yeah. Young.
Oh, I forgot. There's a typo here. This should be a plus sign instead of minus sign. So if you verify this and didn't get this answer, you should be able to tell that it's wrong. It should be a plus sign.
They're like treating like this. Yeah, I think about Halloween is really not all the day, but I'm like Christmas Thanksgiving person because I can take either one. That tastes good, you know? Like Halloween, when people get sick or something. Just eat more candy and so I'm gonna eat more candy.
Make the big signs like the flashlight.
Okay, let's go over the conceptual questions. So question 1 and 2. So analytically verify the concentration profile of an ideal reactor. So these type of word problem, the hardest part is to identify what's useful and what's not useful. So here it sets the context, and then you want to identify what the independent variable and what's the dependent variable. In this case, the independent variable is lambda, which is non-dimensionalized length. And the dependent variable is psi of lambda, which is the non-dimensionalized concentration. So this is equivalent to what we usually call T or X, and then what we usually call Y. So don't let the symbols confuse you. And the second thing is ideal reactor. So we have this first order ODE, d psi, d lambda plus dA. dA is just a constant, no different than alpha, beta, gamma, or something. And times psi is equal to 0. And how do we solve this? This is first order, homogeneous. And I assume it's also separable. So it's equal to minus dA times psi. So d psi divided by psi is equal to d minus dA d lambda. Okay, integrate both sides. And one trick I'll give is that usually you just solve it indefinitely. So you have psi lambda, natural log of psi minus dA lambda plus c, right? And then you solve, you substitute the initial condition, psi of 0 is equal to 1. So this is psi a times e minus dA lambda. So psi of 0 is equal to 1, and then you substitute a, e minus dA. And so a is equal to e dA. And then you substitute back to get the final result. This is one way. But I'll provide another way, another trick. So this trick is that when you have an initial condition and you're doing the integration, you put it in here. So you have psi of 0 is equal to 1. So this is lambda, this is psi. So you put the psi is 1 and the lambda is 0 here. And then you integrate indefinitely to the symbol psi and the symbol lambda. So this becomes a definite integral. So natural log of psi minus natural log of 1 is equal to minus dA lambda minus dA times 0. This is 0, this is 0. So the final answer is psi is equal to e to the minus dA. So now you have verified the result. Any question? The second question is to inspect the governing equation of ideal and non-ideal case. Under what assumption does non-ideal case reduce to ideal case? So non-ideal case is 1 over Peclet number, a constant, times the second order derivative of psi, minus d psi d lambda, minus dA psi is equal to 0. If we move this to the right, we have 1 over PE, psi double prime is equal to psi prime minus dA psi. And this psi prime plus dA psi is the plus dA psi is the ideal case. And the ideal case, it is equal to 0. So now the question becomes, when is 1 over PE psi double prime equal to 0? So this we don't know when it's equal to 0, but we could set this to 0. So the problem becomes, when is 1 over PE equal to 0? It's when PE is very large. When it approaches infinity, 1 over PE is equal to 0. So if the PE Peclet constant is very relatively large, then it reduces to the ideal case. And here it says that Peclet number is the ratio of the convective transport rate and the diffusive transport rate. So when it goes to infinity, the convective force is much larger than diffusive force. So if there's much convection, then it will reduce to ideal case because everything will be homogenized. Okay, any question on that conceptual question? Okay, and the third problem is the numerical solution. How many of you have gone through that question? Problem 3? Not yet, okay. Then please continue and we'll go over it later.
So inside the boundary.
Oh, it's kind of face changes and stuff. There's like face. I don't have face.
It's not the worst case scenario, it's still the.
let's go over this problem. To solve this numerically, we want to first define the ODE. So the ODE in this case is 1 over Peclet number psi double prime minus psi prime minus dA psi is equal to 0. So we want to isolate psi double prime. So move these to the right. We have psi prime plus dA psi is equal to psi double prime move Peclet number to the right. So we have PE multiply everything. So if we write this in a system, we have W0 prime is equal to W1, and W1 prime is equal to this PE times W1 plus dA times W0. So we can write this in Python. So dW0 dt is a lambda function of x, W0 and W1. It is equal to W1. dW1 dt is a lambda function of x, W0, W1. And it is equal to Peclet number times W1 plus dA times W0. And we want to assemble them to a system, and it's a lambda function of x and z, and evaluate dW0 dt at x and unpack the z. The second line is dW1 dt, evaluate at x and unpack the z. And then you can verify if this works with some numbers. And it gives an error saying that Peclet number is not defined. So we need to define the constants. So here we want dA is equal to 2, and PE is a list of 7.5 times 10 to the minus 0, minus 2, 0, and 2. So 10 to raise to the power of NP array of minus 2, 0, and 2 in the brackets. And then let's just define the PE for now. We'll need to do a loop, a for loop. Here it says integers to the negative power is not allowed. So let's make a 10 a float. So that should solve the problem. Okay, next so we can verify this actually works. So next we'll need to define the boundary conditions. The boundary condition is a function, not a list. So y left and then y right. So this is the tricky part because we have a more complicated type 3 condition. So let's review that. Y left has two components. The first component is the original function at 0, the left condition, and the second element is the first derivative at the left condition. Y right has the original function at the right and the first derivative at the right. Because if I were to ask you, if I have an initial condition that contains y0, how do I write it in Python? So y0, first, it is on the left. So this 0 indicates it's on the left. So we have y left. It's a list, so we want to index. What do we index? So this is the 0th derivative. So the original function, so we place it in here. Index 0. If I have y prime of 0, in Python, it's first the left boundary. So y left. And what is the index? It is the first derivative. So we use index 1. If I have y of L, first it's on the right boundary. So we have y of right. It's the 0th derivative, the original function. So the index should be 0. And for y prime of L, it is a right condition. So y of right. It is the first derivative. So the index is 1. Okay, so now we can write our boundary conditions. So the boundary condition we have is already in the form that which something is equal to 0. So 1 minus psi of 0 plus 1 over Peclet number times psi prime of 0 is 0. And psi prime of 1 is equal to 0. So to rewrite these in Python, we write everything on the left. So not including equal to 0. So the first line will be 1 minus psi of 0. And psi of 0 is y left index 0, or y left. That is the left condition, original function. So original function index 0 plus 1 over PE times psi prime of 0. So this is y left index 1 because it's a left boundary condition. Index 1 means that it's the first derivative. So this is the first boundary condition. And the second boundary condition is psi prime of 1. So that's here. Y of right, because it's a right boundary condition. Index 1, because it is the first derivative. So this is the second boundary condition. So in Python, we have 1 minus y left, index 0, plus 1 over Peclet number times y left, index 1. The second boundary condition is y left, y right of 1. And the x, the minimum x is 0, maximum x is 1. X length we can arbitrarily define, say, 1,000 points. And the x is equal to length space from minimum to maximum with 1,000 points. NumP. Lin space. And then we need to define initial guess. The initial guess has the dimension of 2 rows. Each row represents the original function and the first derivative, and then the x length. So 1,000 time points. And we can solve scipy.solve BVP, integrate solve with BVP, the ODE system, the boundary conditions, the x, and the guess. Y right is not defined. So I should have y right underscore here. And the algorithm has converged. And what we are interested in is the solutions, .sol. So this is the BVP solution function. And we can plot these. So fig x is equal to plt.subplots x plot x and evaluate the BVP solution at x. And label this with the Peclet number. And again, we have a mismatch between the shape because the solution we evaluate on x returns 2 lists. And we're only interested in the first one because that's the original function. So we index a 0. So this gives us 1 list. So we need to index 0. So now we have the solution curve. And because we're asked to define it with different Peclet numbers, so we need to use a for loop. And inside the for loop, we need to solve the BVP. So for PE Peclet number in Peclet number list, we want to solve for the solution and then plot the plottings. Notice that if you put the figure axis definition inside the for loop, it will generate 3 figures. But that's not what we want. If we want to plot within 1 figure, move this outside the for loop so it's within the 1 figure. And we can define a legend so that it shows what are the Peclet numbers. And then set the labels. So X label is non-dimensionalized length. and the Y label is non-dimensionalized concentration. And these are psi and lambda. Oh, label. Okay, any question? And then also plot the concentration profile for ideal and non-ideal case for Pecklin number is equal to 7.5. So PE is equal to 7.5, and I'll just copy the solve BVP down here. And we're solving it when the PE is equal to -5. I'll copy the plotting as well. Remove the for loop and plotting the solution for solve BVP. So this is the non-ideal case. And for the ideal case, we already know the solution. So F ideal is equal to a lambda function of x, the NP exp e to the minus damn polar number times x. So these are already solved here, as you verified in the first question. So we can plot that. So F ideal and label as ideal case. And you see that the ideal case starts at 1 and ends at around a very small number. But the non-ideal case doesn't start at 1. It starts at around 0.8 to satisfy the boundary conditions. Any question? Okay, if you have a question, we can stick around and answer the questions. And this is all the content for this lab. I'll see you on Wednesday, tomorrow.
I don't know where that's also why I was like, we could dress up as vector because.
I have this inside.
Wear too tight shirt with no bra.
Because I love that part.
How do you? Coins on it, so everyone pays attention to it, but I don't know where that. Yeah. Those are this skinny has
So look at the. This is what I done. This is how the lines.
Oh.
Wait, you're looking at my. I just know it's like every time.
This is what I have. I was looking at stop and.
So do it another solve it for the
Oh,
system.
yeah.
But that system is
Where's the?
Where is this? I just have a question.
Five
The
hours.
reviewing.
That's what you should do it It's fun. It's just that. I like thinking about it. Guess we have one person. Really? Figure out.
But like, is he proctor? Like, we don't know, it's awesome. Like, you're just an earnest response. I didn't know. Family is fine. Thursday, so I was gonna.
Wait till we.
Maybe 2 weeks ago. Yeah. I've had this band since August. Like now they're like, oh, it's really
He's trying to give us more time to get other.
Ukrainian.
Wait.
Then that we told his last name. Yeah. Oh. So we need these. We thought he was like. He was. Very. I thought that big gap when I saw the baby. That one sounds funny. Like he's best. No, we don't. We don't even know the difference. We don't have to worry. Right? We're coming to the they even.
Oh, yeah.
It's RCP.
There's some,
Or this one?
yeah,
Thank you.
last question.
See you.
I somehow got this. I don't think this is right.
Mm,
I think there's something wrong with the bound, but I can't really figure out what's.
yeah, let's look.
Okay, I'll fix it.
Okay.
Thank you.